particular way. And so that'll be a lot of what we talk about for the next, couple of months in this particular class. Okay. So now what I want to do is I want to kind of end this particular lecture. I've already talked more than I meant to, but we're going to end this particular lecture by taking you through a very quick and simple regression exercise. And in doing so, what I will show you is a little bit of a taste of kind of applied economic research. And for some of you, this may seem very comfortable. You may have seen something like this already. And for others of you who maybe have not had an econometrics class and have less of a statistical background, some of this might seem a little bit new. Suffice it to say, the stuff that we talk about in the last part of this lecture will be reviewed several times over the coming weeks. And we'll look at not just in this particular example, but using other data sets as well. So we're going to go through this several times. So no worries there. Okay, one of the things that I really, really encourage students to do is to, from the very beginning, get used to using what we refer to as do files. Do files are code that you can save. And what this allows you to do is it allows you to rapidly run your code quickly, time in and time again. One of the things that students often misunderstand about running regressions and doing statistical analysis is how many times you're going to do the same thing over and over and over again. Students kind of often have this very idealistic view of running regressions where you never run a regression until you've decided what your exact perfect one is, and then you hit enter on that regression, and then there it is. There's your regression, and you're done. It's much more, of a sort of process of elimination. Applied economic research is really exploratory. You're exploring both the data that you're using, the data sample that you've collected, as well as the regression techniques. You're using all of those things to, make sure that your statistical analysis is being carried out in an appropriate way. And again, that'll be a lot of what we talk about in this course is what is the appropriate statistical strategy given a particular set of statistical problems, right? And the main one we're going to talk about here is omitted variable bias. Okay, so if we look at my do file here, you'll notice that I have a set of 5 commands here at the top. These are going to show up in every single do file that I produce, so they're not specific to this particular example. This first command changes my working directory to a particular folder. In this case, that folder is on my desktop right here, right there in the middle. So everything that I do within Stata that I save is going to be saved to that particular folder. Where you put your work and where you organize your things is very, very important. It took me a long time as a researcher to realize how important it is to have well-organized workflow and using do files and understanding where your work is being saved in terms of your working directory is crucial. Okay, so whatever the project is I'm working on, I always create a separate working directory for that specific project. And then that way I can keep everything nice and clear. Okay, the second command just simply clears the Stata command. So if there's any existing Stata routines that are being run, that's going to clear them. The third one, set more off, is simply when you do things in Stata, there's this annoying thing where it doesn't keep going. It gets hung up. There's a sort of more, and you have to click the space bar to keep it going. If you put set more off there, it takes that away and it just runs your entire code without stopping, which is nice. And then this last bit of code here, this is just, if we have any log files open, it will turn them off. And the reason why we put this here is because in addition to the do file, I'm also going to be producing a log file. And I'll explain a little bit about what the log file, why we use the log file in just a moment. Okay, before we hit this particular example, we need to download and install these packages within Stata. And so you can actually just put these directly, these commands directly into Stata. And so, for example, this is going to install the bcuse command. The bcuse command is a command that allows us to bring up data sets which are stored on this specific website. I'll talk a little bit more in class about that. We're probably not going to use this particular, command. So actually, let me just go ahead and get rid of this now because we're not going to use it. We'll use that. That'll be something we talk about next week. And then we also use the est out package. That's actually going to enable us to make nice tables of our regression. Okay. So once you've installed the bcuse command, you'll be able to call the data up using this particular bit of code. So bcuse wage 1. This is going to upload a data set in Stata, which is an old data set. It's kind of a classic data set, in which there is a cross-sectional data set on individuals, their wages, their education, their experience, their tenure, whether they're white or not, whether they're female or not, married or not, so on and so forth, how many dependents they have. There's a lot of different variables here. We're not going to pay attention to most of them. We're only going to pay attention to 3 or 4 of them in this particular example, but suffice it to say, this is a data set where we have individuals and we have their characteristics, including specifically their work characteristics, their wages, and other work characteristics and things like that. And again, remember the goal of what we're doing here is we're going to test the hypothesis that education has a causal effect on wage. And beyond that, beyond whether there is an effect, we're also going to measure the specific effect. So if there is a significant effect coming from education, we're interested in precisely what that effect happens to be. Okay, so we can summarize our data, which just gives us a little bit of information. Again, it's really important that you know what's going on in your data. So the summarize command is just going to give us the basic information about each variable in the data set, the mean, the standard deviation, the min, and the max. You can get more detailed summary statistics on your data if you want to, but this is usually a good start. We'll talk a little bit more about those more detailed versions later on. The first thing that you want to do is you want to kind of understand the distributions of your data. So for example, how is wage distributed in our data set? What does it look like? So to do that, we can just produce a very simple histogram, hist wage. When we do that, we get this nice little graphic, which shows us the behavior of wage within our data set. We can see that the data is sort of skewed downward. In other words, we have more individuals at the lower end of our wage scale than we do at the high end, which is completely typical. This is actually fairly representative. One of the concerns that we might have, this is a bit of an aside, but one concern we might have is that the distribution of our data is not representative of the distributions that would be seen in random pools from society. In other words, our sampling creates a non-random distribution of wages. Looking at this, this feels like it's pretty representative of the way wages are typically distributed. But if you are doing a project in which you're looking at wages or median wages or anything like that, you want to kind of see, you want to kind of make sure that your data is representative of some sort of basic statistics and things like that. Here, wage looks like we would expect it to. I can run these other 2 commands. These are actually going to save that particular histogram as first a static graph and then second as an actual picture so that I can go back and look at it later. So if I, just to kind of give you a look at that, let me get here. So we go to wage hist. And so if I ever want to go back and I want to look at that particular graph, I can. I also have saved that as a PDF. with that second line of code, which again, just gives you some information. You don't have to always go back and rerun your code. You can save these and then kind of, one of the things that I like to do as a researcher is, like, if I'm doing something on a computer, I oftentimes like to print it out and then get off the computer and kind of, with my hands and be more physical with it. And so I like to do this kind of stuff and print these various things out. Okay. Okay. So let's look at the histogram of education. So we saw that wage was skewed downward. Let's look at education. A little bit kind of different, kind of on the opposite end. So it's kind of skewed upward maybe a little bit, although it looks, fairly normally distributed. We can see that the most amount of education right here is that 12-year high school degree cutoff. So we can see almost everybody has at least, most people have just a high school degree, and then a lot of other people have college degrees and advanced degrees and things like that. It's really important to note that education here is years of education. So 1 year, 2 year, 3 year, 4 year. And so 12 years of education is a really important, because that's high school completion. And then 16 years of education. So you'll notice there's humps at each of these kind of milestones, right? So people and that is something that when we extend this example in future weeks, we'll talk about the potential for these kind of humps to maybe matter, and how we might want to think about them. Okay, so again, we're kind of seeing already that most people have low incomes, and most people in our sample only have high school degrees. So we're already kind of uncovering a little bit of a relationship there. Obviously, we haven't done any sort of statistics, and so therefore we don't know for certain, what that relationship happens to be. So next thing we'll do is we're going to run a scatter of wage and education. And so this is just going to show us education on the horizontal, wage on the vertical, and we can kind of see, again, we're sort of visualizing what's going on in the data. We haven't run a regression yet, but we can already sort of start to see that it seems like the more education someone has, the higher their wage tends to be, right? And again, we're going to test for that in just a moment. One thing to keep in mind, and again, we're going to sort of talk more about this in a moment, is there's a certain, tendency for us to forget that whenever we run a regression, just basic ordinary least squares, that what it assumes is that the underlying relationships are linear. Okay, when in fact underlying relationships may not be linear. And there is some reason to look at this graph here and start to question whether education and wage are linearly related. Okay, that's all I'll say for now. Okay, now what we're going to do is we're going to fit a line to that scatter. So this actually does run a very basic ordinary least squares regression and fits a line. So it scatters the data and then fits that line. And we can see, unsurprisingly, that when you fit a line to this particular data, it is positive, so that the inferred relationship between education and someone's wage is positive. Okay, and again, we haven't talked about specific effects, but again, this is perhaps unsurprising. Now remember, ultimately our goal is going to be to test the hypothesis that education is statistically important to someone's wage. We could take another step and say the hypothesis could be whether education positively affects someone's wage, or we could leave it as just general, does education affect wage? And then whatever the sign, whether it's positive or negative, again, it's probably going to be positive, whatever the sign happens to be, that's what it happens to be. Students oftentimes frame it as strictly positive or strictly negative if they assume it's strictly positive or strictly negative. It's usually better to leave it general. So does education have an effect on wage, and leave it at that. That's a much simpler hypothesis for us to test. Okay, let's just run a simple correlation between wage and education that produces the covariance matrix. So let's go to our output. So when we run a covariance matrix between wage and education, we see a sizable amount of covariance between the two variables. Again, more evidence that there is a potential relationship between education and wage, although nothing causal yet, right? We can't say anything causal about education and wage by simply looking at a covariance matrix, but we can see a couple of things. First off, that they do seem to move at the same time. That is, that when changes in education occur, we expect to see changes in education. And we saw from our previous line fitting exercise that those effects appear to be positive, as we would expect. Okay, so now we're going to run our first regression, and we're simply going to regress wage on education. Now, what I'm going to do here is, instead of running the regression on wage, I'm going to use the log of wage. We'll get into more specifically what this means later on and why we do it, but for now, suffice it to say that by using the log of wage, we are making the interpretation of our coefficient estimate a lot easier. So let's run this particular regression. All right, so when we run this regression, we can see that the estimated coefficient for education's effect on wage is that for every additional year of education, wage rises by about 8.3%, 8.27 or 8.3%. When we log the left-hand side variable, and again, we'll formalize this more later on, when we log the left-hand side variable, then the interpretation of the coefficient estimate here is that for every 1 unit increase in the right-hand side variable of interest leads to a coefficient percentage change in log of wage. So we just move the decimal over. So again, this tells us that for every additional year of education, we expect wage to be 8.2 or 8.3% higher, which is quite a bit, economically meaningful. We also see from our T statistic that this effect is significant. Just the quick and dirty rule is you want your T statistics to be greater than 2. If your T statistics are greater than 2, you have good levels of statistical significance. If they're less than 2, you're starting to get closer to non-statistical significance. Obviously, a T statistic of 10.9 is huge. And so not only do we measure the effect to be 8.2 or 8.3 rather, but it's also statistically significant. So again, this is not a causal model. This is a correlation model, but we can see that there is a positive correlation being estimated here, and that an additional year of education is associated with 8.2% or 8.3% rather higher wage. Okay, what we can do is we can run essentially what attempts to mimic an omitted variable test. We're going to test to see whether variables were being omitted from that particular regression. Now, I'm not going to get into too much detail here. Technically, the of test, which is what we're going to run in just a moment, is what we call a reset test, R-E-S-E-T, a reset test. It's not technically, truthfully, an omitted variable bias test, even though it's called of test. What it actually does is it tests for the zero conditional mean assumption of our regressions. We'll talk more about the zero conditional mean assumption later on, but for now, suffice it to say that we assume that our errors have zero conditional mean. And what the of test essentially does is, within the context of the variables that we include in our regression, it tests whether we have zero conditional mean with respect to those particular variables. So it tells us whether we have an underlying problem in our model that might be solved by adding more variables to it, more explanatory variables. All right, so we run this of test, and we get these results, okay? Now, whenever you run a test, it's a statistical test, all you're doing is testing a hypothesis, okay? Here, the hypothesis that you're testing is that the model has no omitted variables. And you actually can see that that's it says it right here, right? The model has no omitted variables, okay? Just like any other sort of test of statistical significance, what we are interested in is the p-value. Okay, and this is the p-value for this particular test. If p-values are less than 5%, 0.05, then we fail to reject the null. Or excuse me, we are able to reject the null in that scenario. And so whatever the null is, we find the opposite of that. Okay, in the regression model, if you'll recall from your statistics courses, you'll know that the null hypothesis is always that there is no effect, right? So the null hypothesis here is that education does not have an effect or is not correlated with someone's wage. Because our p-value is less than 0.05, which in turn is related to the fact that we have a high t statistic, then we know that we can reject the null, and therefore education is correlated, or potentially education has a significant effect on somebody's wage. In the of test, it's the same thing, okay? The null hypothesis is there's no omitted variables. We can see here that the p-value is way less than 0.05, so we can reject the null, which is usually a good thing. But when the null is you have no omitted variables and you reject that null, it means you have omitted variables, which is not surprising, right? We kind of know that there's omitted variables in this model, but it's good to kind of have that confirmed. Okay, so now we're going to add experience to our model, just like we had previously talked about. So we run this model, again, log of wage being regressed on education and experience. And experience is years of experience. And these are the results we get. Okay, we can see that in fact the estimated coefficient on education is higher than it was before. What this suggests is that in the model where experience is not included, the bias on education is downward. In other words, in the initial model where we have omitted variable bias, the effect was about 8.3%. In this model, where we've potentially removed some omitted variable bias, at least specifically with respect to experience, we can see now that the effect is almost 10%, right? 9.8%, which is higher. It's still statistically significant. In fact, T statistic is even higher now. And then if we look at the coefficient on experience, we can see it's also positive. So more experience means higher wages. We can see the effect is about 1%. So for every additional year of experience, we see that someone's wage rises by about 1%, significantly less than the education effect, but not zero, which is important. And we can see that the T statistic is above 6. So this is statistically significant. So experience matters. And when we put experience into our model, we actually get a larger causal, or I'm sorry, a larger marginal effect coming from education than we did previous. Okay. Now, in future weeks, we'll talk a little bit about how we could have predicted that. We could have predicted what the bias would have been, but for now, I think it's just interesting to point out that by not including experience in our initial model, we in fact underestimate the effect of education. And I think you should think about why that is. Why would not including experience into a model cause us to underestimate the effect of education? Okay, so let's check our of test after that regression. And okay, so we still reject the null, but we can see that the p-value is increasing. So we still reject the null, it's still less than 0.05. However, we can see that we've perhaps mitigated some of the omitted variable bias, but clearly there's still omitted variable bias. So now what I do is I run that same model, but I include tenure. And again, tenure is the amount of time someone spends at a single firm. Okay, So we run this regression, and we see that, well, first off, we see that the effect on tenure is positive. It's about 2.2%. So for every additional year of tenure someone has at a company, their wage is about 2.2% higher. So the effect is larger than the estimated effect on experience. And we can see that the t-statistic is very large, so it's statistically significant. And we can see that the coefficient on education is pretty similar, although somewhat slightly smaller. So by not including tenure in our previous model, we were biasing education upwards a little bit now, right? So you can see that when we include experience, the effect of education goes up. When we include tenure, the effect of education declines a little bit, right? So what we're doing is we're trying to zero in on that specific causal effect of education. And by reducing omitted variable bias, what we are doing is we're getting closer and closer to that sort of random controlled trial style of regression. We're getting closer to reducing confounding, right? Now, we're never going to get to the full random controlled trial with observational data. It's impossible. But we can mitigate the presence of omitted variable bias and get closer to estimating real causal effects by thinking long and hard about the data generating process and by including quote unquote control variables in our model. So this is what a lot of what you're going to do. So whenever you're thinking about your particular topic, you think about not only the effect that the main variable of interest that you has on the left-hand side, the dependent variable, but what are the other components of the data generating process that you need to be aware of that could potentially confound your results. All right, lastly, we'll run the of test for this last model, and we're very, very close, right? 0.0048, almost 0.05. It's getting there, right? We're reducing omitted variable bias, at least in the context of this particular test. And so, but we still have it. So like I said in the previous part of the literature, in the lecture rather, one of the things that can cause a sort of similar thing to omitted variable bias is what we call model misspecification. The most common form of model misspecification is the fact that non-linearities exist, but I haven't included them in my model. So far, we have only run models which have assumed linearity on the right-hand side, education, experience, and tenure, okay? But what if there are non-linear relationships potentially? What can we do about that? Remember this particular graph that we saw before. Remember this. Remember I said that if you force a linear line there, it's gonna estimate it for you. And here we see it's positive. If you just look at that data, it looks like there might be a non-linear relationship between education and wage. What do we do about that? Well, it's very similar to omitted variable bias. If we think that education and wage have this non-linear relationship, it's actually a very simple fix. We're just going to include into that model a square of education. So we include in the model education. We also include in the model a square of education, okay? In order to do that, we first generate the square of education. So it's just literally education times education, right? And then we run this particular model. Now, again, we're going to talk more extensively about nonlinearity. So we're going to cover the basics of this and the ideas and the concepts. So if you're a little bit like, well, wait a minute, why are we doing this? We're going to cover it in more detail in the future, but suffice it to say, what we're doing right now is we're exploring how we can reduce omitted variable bias, and putting experience and tenure into our model have not cut it yet. Okay, so instead of just sticking some more variables into the model, let's look at maybe a misspecification problem and see if that happens to be the case. Okay, so I put the square of education into the model. I run the model, and what I find is very interesting. First off, I see that when I put education squared into the model, that I get this negative effect on education. It's not statistically significant, but it is interesting. Okay, and then I see that the square is positive and it is statistically significant. Okay, so what does this mean? Okay, well, think back to your math days, and specifically when you were learning about functions. Okay, if you take the first derivative of a function and it's negative, it tells you that generally that function is moving downward. And then if the second derivative is positive, then there's this change, right? And so in this particular scenario, what we're picking up on is that it isn't so much education, years of education, but it's as you attain more and more and more and more education, that education matters more. So early years of education don't matter very much at all, but later years of education, college degree, master's degree, Ph.D., these things matter, right? So kindergarten through fifth grade has very little economic impact. Bachelor's degree, master's degree, these have a much larger impact. Okay, and that's kind of what this regression outcome would suggest to me. What we can do is we can fit a line to see if the relationship is nonlinear. The only difference between this and the graph that I produced earlier is that instead of the L-fit, I have Q-fit CI. So this is going to fit a quadratic line. So it's going to be a nonlinear line. And it's going to produce a confidence interval as well. So let's look at that. And as you can see, this is exactly what I was just saying. Early parts of education don't matter at all. In fact, there's some sense that there's a little bit of downward trajectory here. But then as you start getting more and more and more and more education, we see that effect start to increase. So in this scenario, it isn't so much each additional year of education matters until you have a sizable amount of education. And so in other words, education would exhibit increasing returns, right? As opposed to diminishing returns, right? Where we would see the effect of education decrease a little bit over time. Here we see the effect of education is in fact increasing. So the more and more education you get, the better it is for your bottom line, so to speak. Okay. So lastly, the last thing that we're going to do is we're just going to put all of these into a very nice table so we can see all of the regressions at once. And so I'm going to run this whole chunk here. I will obviously share this do file with you so you can replicate it very, very easily inside of Stata. Make sure before you try to produce the table that you have installed the EST OUT package that will enable you to run this. Okay, so we're going to run this. If you put in the code here, .rtf in your ESTTAB command, it's actually going to spit out a Word document, which makes your life a lot easier. Again, we're going to do this a lot in class, so if you're not picking up on this immediately, it's completely okay. All right, so we run that code, and we see right here, it says output written to lecture.rtf, and we actually see that this is clickable. So we just click this. Word fires up, and there we go. So we have 4 regressions. All of them have log of wage on the left-hand side as the dependent variable. This first model only considers education on the right-hand side. The second model considers education and experience. This third model adds tenure to that model. And then this fourth model, if you'll remember, includes the square of education. And again, the reason why we put the square of education in is because we were concerned that education and wage have a nonlinear relationship. That amounts to omitted variable bias. So if there's a nonlinearity going on between your variable of interest and your left-hand side variable, not taking care of that nonlinearity biases your coefficient estimates. So in the same way, not putting a variable in would bias it, so would not taking care of a nonlinearity. And it just so happens to be that the way you take care of a nonlinearity is you include a square of the variable into that particular model. So what have we done? Okay, so if I was writing a paper where I was estimating the effect of education on wage, this would be a table that I would probably want to put in that particular paper. The reason why is because it gives my readers 4 different regressions to ponder. Each of the regressions exists for a particular reason, right? Each of the 3 models after the initial one are trying to reduce the omitted variable bias that we saw in our reset test, our of test. And so, you know, these are our 4 models. And at the end of the day, the analysis would conclude based upon these numbers, and if I believe these numbers are true, is that education and wage are generally positively related. However, early years of education are far less economically meaningful with respect to wage than later years of education. Now, arguably, that's a little bit tough to say because you can't have later years of education without early years of education, but rather, if you only have early years of education, your wages are probably going to be quite low. And if you also have higher levels of education, your chances of having higher wages are much higher. So education and wage are positively related, but it's a non-linear thing. Which given the skewness of our data on the wage side being skewed downward and the skewness of our education data being skewed upward, it's not very surprising at all that there happens to be a nonlinearity in there. And you're not everyone's going to have a nonlinearity that exists in their particular model, but I just want to show you that in the pursuit of reducing omitted variable bias, we are going to consider the potential problems, and the potential problem that we solve in that 4th model is that there's a nonlinear relationship between education and wage, and we indeed did find evidence of that. So lastly, let's run the of test for that last regression to see if it passes the omitted variable bias test. And you can see that since we've included the square of education, we are now able to fail to reject the null, which means that now, at least from the perspective of this particular test, we're being told that we no longer have omitted variables. So, right, this is the process of being a researcher. So once I felt confident about the results that I found, once I felt confident that I had appropriately approximated causal effects, I would write up the paper at that point, right? And so this is what you're going to do. You're going to collect data, you're going to strategize a particular regression technique or set of techniques, you're going to estimate causal effects, or you're going to estimate correlations and descriptive statistics, and then you're going to write about them. You're going to explain what topic you're writing, the data that you collected, the empirical strategy that you used, and the results that you found, right? That is applied economic research. That is what we do as economists. And increasingly so, this type of analysis is being carried out not just by academic economists, but by private industry as well as public industry. And so again, the skills that you'll develop in this class are particularly useful. All right, that's going to be it. This lecture was a lot longer than I anticipated it being, but I think I covered a lot of useful information. And again, remember that we have observational data, but that doesn't mean that we have to give up on the ability to estimate causal effects. It just means that we have to be very careful, and we have to consider a lot of things in order to be able to do that. And kind of the top line problem of causal effects is the issue of omitted variable bias. And again, I think that we did a good job of covering that. So until next time.